And I would like perhaps to let the committee introduce themselves.
So,
Introduce Travis.
okay, so I'm Secret Closer in the Space Environment Solid Systems Laboratory. Fortunate to have Professor Marco Pavone, Professors and Martin Lowe. So I would just like to say a few things about Travis before turning over the floor to him. So Travis comes to us from the University of Minnesota, where he completed a degree in aerospace engineering and mechanics. I had to ask you this morning, is there an aerospace engineering without mechanics?
No, it's just what they call it at Minnesota.
Okay, all right. And he graduated with high distinction, and I first met Travis while teaching graduate dynamics. This was quite a few years ago, and I remember Travis asked the toughest questions with Andrew, and thinking, wow, this student has a really bright future ahead of him, and never thought actually that he would end up in the laboratory. And the reason why is, as you all know, what Travis is doing is not really core to what we do in the Space Environment and Solid Systems Laboratory. But he was really fortunate to connect with Dr. Martin Lowe at JPL, who's a world expert in this. And through his brilliance, through his creativity, through his own initiative, he was able to win a NASA fellowship and do some outstanding research, which you will hear about today.
Well, thank you very much for that introduction, and thank you all for being here today. I'm so excited to be sharing my PhD research on the dynamics of multibody system. Where here, multibody refers to regions in space where the competing gravitational attraction of multiple primaries is significant simultaneously. A great example of this is Jupiter and the Galilean moons. What you're seeing is the moon Europa as it makes a transit across the red eye of Jupiter. Now, there's been a growing interest in missions to these systems in recent years because it's believed that Europa, Ganymede, and Callisto all have subsurface liquid water oceans with the potential to harbor life. To address this interesting possibility, a number of missions are planned for the upcoming decades, and they all have something in common. They have very complex mission architectures, and as such, they demand innovative trajectory solutions which leverage the dynamics of the multibody environments that they're in. Now, we need a deeper understanding of these multibody dynamics if we're to meet the mission requirements. One of the places we can look for inspiration is nature, where comets and asteroids reveal low-cost pathways through space we may leverage in the design process. Of course, understanding the trajectory of comets and asteroids is an interesting and important question in its own right, particularly for assessing the risk of impact. What you see here is the comet Shoemaker-Levy 9 as its various fragments impact with Jupiter in 1994. You can see one of the explosions here in the lower left. If you add up the energy of all these fragments, it's equivalent to the detonation of 6,000 Tsar bombs, the largest hydrogen bomb ever created. So the reality of this threat is sobering, and knowledge of multibody dynamics will help unravel the mysteries of solar system bodies like Shoemaker-Levy 9. Now, in both this dynamical astronomy and our mission design application, knowledge of the multibody dynamics may be achieved through a study of the underlying dynamical structures, namely invariant manifolds. So the focus of my investigation and my talk today will be on understanding the role of invariant manifolds in controlling these dynamics. The rest of my talk will be organized as follows. I'll begin with an introduction where I'll cover the dynamical models I use in my analysis, and I'll also cover a summary of the important previous work done to understand this, or you can better contextualize the contributions I'll be presenting today. From there, I'll do a study of the topology of the transit orbits and of the equilibrium region in both the planar 3-body and planar 4-body problems, where I will demonstrate that invariant manifolds actually govern the flow over a much larger range of energies than previously proven. I'll then take these insights and apply them to a practical real-world example in the form of the Europa lander mission design, where I will leverage structures of both the 3-body and 4-body problem to design capture, landing, and end-of-life trajectories which significantly outperform our 2-body baseline designs. Finally, I'll summarize my contributions and discuss some areas for future work. All right, so let's begin by taking a look at the planar circular restricted 3-body problem and planar circular restricted 4-body problem. So if you draw your attention to the left-hand plot first, in the 3-body problem, we model the motion of an infinitesimal particle P under the gravitational attraction of two massive primary bodies, M1 and M2, and we ignore all other forces. We constrain M1 and M2 to move in circular orbits about their common barycenter, the center of mass of the system. And we use a rotating reference frame with its origin at the barycenter and allow it to rotate such that the primaries lie on the x-axis for all times as indicated here in the figure. Now, as will be seen shortly, we use this rotating frame because dynamical structures emerge in the rotating frame which are not present in the inertial frame. In the case of the four-body problem, today I will be treating it as a perturbation to the three-body case. So we'll use the same frame of reference and setup for masses m1 and m2, and simply add an additional gravitational perturbation here, another primary m3, which will pull on our infinitesimal particle p. I will assume that m3 moves in a circular orbit about the m1, m2 barycenter, and that it does not affect the motion of m1 and m2. So in this configuration, the equations of motion are well known as stated up here, where the omega is the effective potential function. To arrive at this system of equations, I've had to non-dimensionalize the system, as is traditionally done, by choosing a length unit such that the distance between the primaries m1 and m2 is unity, and such that the non-dimensional period is equal to 2 pi. In doing so, Newton's gravitational constant and the angular velocity of the rotating frame become 1, and we get this expression here. In the case of the three-body problem, our effective potential function is given as follows, where you can see actually this first term corresponds to a centrifugal force term. There's a Coriolis force term as well in the equations above, and the last two terms correspond to your standard gravitational attraction, where mu is the mass parameter. Now in the case of the four-body problem, we simply have to change our effective potential function to include one additional term that accounts for the perturbations of m3. Now, as I had mentioned before, we use a rotating frame for patterning evocation. That's because in the rotating frame we have one integral of motion, the Jacobi integral, which corresponds to the conservation of energy in that rotating frame. Now, there are no general solutions to these nonlinear equations of motion, no algebraic solutions. However, we can get a great deal of insight into the qualitative nature of flow by looking at certain dynamical structures. So we can begin with the Lagrange points. These are equilibrium points in the space. So if I park a spacecraft here with zero velocity, it will remain there for all time. Now, these are particularly important regions because around these points exist families of periodic and quasi-periodic orbits and their associated invariant manifolds, and these structures will reveal a lot about the nature of the flow. So now I'm going to take a zoom in around these points to classify some of the trajectories I'll be talking about today. So first, at a given Jacobi constant, a given energy level, there exists a region in space where motion is not physically permitted, shown here in gray. It's known as the forbidden region, the boundary of which is called the zero velocity surface, the locus of points where velocity vanishes. Now you can observe that the forbidden region divides the space into different realms of motion. The area inside we call the interior region, the area outside the exterior region, and the area here around the second primary, in this case Jupiter, we call the temporary capture region. Observe too that it forms a neck in the space near the Lagrange points. We call that region the equilibrium region, shown here on the right-hand side. So if we zoom in here, we can classify orbits into 4 categories depending on their behavior. In red, we have transit orbits, those which cross the equilibrium region. In blue, we have non-transit orbits. They remain on one side for all time. In black, we have repeating orbits, so closed periodic solutions here. And then in green, we have an asymptotic orbit. So these are orbits which converge or diverge from the periodic solution. Now these are particularly important because they form pieces of the stable and unstable manifolds, which in turn form the basis of multibody analysis and design. So what are these invariant manifolds? They're powerful structures which appear in nonlinear problems, and actually everyone in this room has worked with them when they studied the basic pendulum problem. I have the phase portrait of the pendulum here in the upper right-hand corner. The points at pi and minus pi here correspond to the inverted pendulum solution. That's an unstable fixed point hyperbolic in nature. So we have flow which is attracted to this solution, the green arrows here, and flow which is repelled from that solution, indicated by the orange arrows. We call that attracting flow the stable manifold, and that repelling flow the unstable manifold. Now the important observation in the pendulum problem is that it acts as a separatrix of motion. That is, it separates 2 distinct classes of flow. Those orbits contained within the manifold correspond to bound oscillations, while these orbits contained outside the manifold are unbound in their oscillations. So it separates 2 important classes of trajectories. In the case of the three-body problem, we have very much an analogous picture, where now instead of an unstable fixed point, we have an unstable periodic orbit, and we have sets of trajectories which diverge from the periodic solution, the unstable manifold, and sets of trajectories which converge to the periodic solution, the stable manifold. And you can think of these manifolds as governing flow in the equilibrium region by drawing and repelling flow from this space. Now, Conley in the 1960s observed, just as we see in the pendulum problem, these manifolds too act as separatrices of motion. transit orbits must go through the invariant manifold tubes. So the manifolds are separating the transit and the non-transit orbits. Now there is a caveat to that theorem, which I'll be diving into shortly, but the takeaway here is that manifolds systematically map out space. They identify useful orbits in analysis and useful orbits in design. So let's take a closer look at some of the important works over the years that have been done to understand the role of invariant manifolds in governing the flow of the equilibrium region. So as I just mentioned, Conley laid the foundational work in the 1960s, and through a study of the linearized equations of motion, he proved that transit orbits must travel through the invariant manifold tubes. However, very importantly, he proves this only for energies, quote, close to the equilibrium region. He also describes these as low energies, or energies very near the equilibrium point. However, he makes no attempt to quantify what that energy range is, and prior to my investigation, it remained unknown. In the 1970s, McGehee built upon the work of Conley and developed a representation of phase space using a spherical topology that allows one to visualize the manifolds directly in the energy surface. Now this gives a great deal of insight into the role of manifolds. However, his visualization is only applicable at low energies, again, energies close to the equilibrium point. In 2005, Mokel studied high energy orbits and proved the existence of high energy transit orbits, but makes no comments on the role of invariant manifolds or other dynamical structures in governing those trajectories. And then finally, Gianconti, Pontani, and Teofalato in 2014 developed a representation of phase space similar to McGehee, but they used a pipe topology. This has the advantage of being applicable across all energy levels. However, they only look at heteroclinic connections. They do not look at the role of invariant manifolds in controlling the flow of the equilibrium region directly. So the work I'm going to show you today most directly builds off Conley's foundational theorems. So I want to take a closer look at what he did to better identify the gaps in knowledge. So as I mentioned before, Conley studied the linearized equations of motion, and in this case, we do have general analytical solutions. And with those solutions, Conley is able to make this sketch of the equilibrium region. So this x here at the center, this point corresponds to your Lagrange point. It's surrounded by a Lyapunov orbit here. The bounding hyperbolas at the top and the bottom correspond to the zero velocity surface, the boundary of the forbidden region. The strips labeled S1 and S2 here bound projections of the asymptotic orbits, so the invariant manifolds lie in this space. Now, the general solution Conley found is given here, and I basically just want to draw your attention to the exponential terms, and specifically to the coefficients alpha 1 and alpha 2. Now, Conley observed that he could classify trajectories in the equilibrium region depending on the sign of alpha 1 and alpha 2. So for example, if alpha 1 and alpha 2 have the same sign, the orbit will be a non-transit orbit. Moreover, he realized that in certain regions of configuration space, the sign of alpha 1 and alpha 2 is independent of any system parameters. So for example, right here, both alpha 1 and alpha 2 are positive, thus any trajectory which passes through this region of space cannot make a transit of the equilibrium region. Moreover, he realized that far from the equilibrium region, the only place in space where this transit criteria can be satisfied is inside these strips labeled S1 and S2. So this is his key observation. He realized that in order to cross the equilibrium region, transit orbits must be inside the invariant manifold tubes. Now, the reason that this result is so profound and important in our field is that the picture he draws here, the linear case, is actually homeomorphic to the nonlinear equations of motion. So what is a homeomorphism? It's a mapping which preserves all the topological properties of a space, such as connectedness, compactness, and separation axioms. So the takeaway here is because of that homeomorphism, in proving it for the linear case, he's actually proving it for the full nonlinear equations of motion. So it's a very powerful result. Now, I mentioned there was a caveat before. This homeomorphism holds only for what he calls, quote, suitable energies. But again, he makes no attempt to quantify what suitable means. He describes them as low energies or energies close to the equilibrium region. But this result is the theoretical justification for the multi-body analysis and design tools that have been built since Conley. So it's very important that we understand what this energy regime is. And that brings me to my problem statement. My goal is to understand the role of invariant manifolds in controlling transit orbits of both the planar 3-body and planar 4-body problems. Now, in the case of the 3-body problem, I want to understand the energy range over which Conley's theorems hold, as well as more generally over what energy range do manifolds in fact govern the flow. In the case of the 4-body problem, we actually don't have any strong theorems on this subject at all, so it's very much an open research question. I also want to take these insights and apply them to practical examples from dynamical astronomy and mission design. So here are the contributions that resulted from my investigation. So number one, I set an upper bound on the energy range over which Conley's theorems hold. So I will demonstrate today that they do in fact break down. But then more generally, I'm able to show that manifolds of the three-body problem actually govern transit orbits over a much larger range of energies than previously proven. Second, I derived a method to approximate the four-body problem as an effective three-body problem of a perturbed energy level, and show that the manifolds of that effective three-body problem actually govern the transit orbits of the four-body problem. Third, I demonstrated that invariant manifolds controlled the capture of comet Shoemaker-Levy 9, which ultimately led to its impact with Jupiter in 1994, as we saw in the video earlier. Fourth, I leveraged dynamical structures of both the three-body and four-body problem to design capture, landing, and end-of-life trajectories for the Europa lander mission, which significantly outperformed our two-body baseline designs. And then finally, I was able to improve state-of-the-art differential correction algorithms by employing modified Chebyshev-Picard iteration and realized an order of magnitude improvement in computation time. Now, I'd love to discuss all of these with you today, but we're unfortunately quite time constrained, so I'll focus my talk just on these bolded contributions here. With that, let's dive into the topology of transit orbits in the three-body problem. Now, we would like to visualize the manifolds and trajectories directly in the phase space because that is where they evolve. The phase space is four-dimensional, but due to our one integral of motion, the Jacobi integral, we can reduce that four-dimensional phase space to a three-dimensional energy surface, which makes visualization feasible. The unfortunate part is that due to the functional nature of the Jacobi integral, in general, any three of the coordinates will only resolve the magnitude of the fourth coordinate, but not its sign. As a result, we have ambiguity in our visualizations. A great example is shown here in the figures, where we have a transit orbit here in blue crossing the equilibrium region, and a manifold here in orange and green. If we plot this manifold in the phase space via the Jacobi integral, we get this picture here. Now, it appears that this trajectory is piercing the side of the manifold tube rather than entering through the generating Lyapunov orbit here. Now, this appears to be a contradiction of Conley's findings, but that erroneous conclusion is actually the result of using an improper topology to visualize this space. To think of it another way, it's like trying to visualize the Earth on a planar map rather than on the sphere. The natural topology of the Earth is a sphere, and when you try to project it onto the plane, you are not preserving the metric, and that projection does not faithfully capture the geography of the Earth. So too, we're trying to visualize the manifolds with an improper topology, so this visualization does not qualitatively capture the nature of these dynamics. So our solution is to find that mapping which does represent the topology, and that is a cylindrical isomorphic mapping. We can observe that in the equilibrium region, the topology of the energy surface is homomorphic to a strip cross a ring. So the strip comes from configuration space, where we take those bounding hyperbolas, the zero velocity surface, and we squeeze them down until you get a strip in position space. Now, via the Jacobi integral, at each point in configuration space, there's a unique velocity vector magnitude, but there's freedom in the velocity vector angle. So at each point in space, there's a ring of possible velocities, seen by the equation x dot squared plus y dot squared equals v squared, where v here is the magnitude. The product of a strip and a ring is a pipe, the space between two coaxial cylinders. Now, you can see this by taking the volume of revolution of your strip through that ring to produce the pipe. If that's not intuitive, I'll be showing an animation on the next slide which makes this clear. But for now, I want to first draw your attention to the homeomorphic mapping itself. So x tilde corresponds to the variable along the axis of the pipe. That's simply our natural x. We're trying to keep this space as intuitive as possible to work with. In that same regard, r, the radial variable of the pipe, corresponds to y, and then theta, the angular variable of the pipe, simply corresponds to our velocity vector angle. So let's see the construction of this space in an animation. So we can begin in our equilibrium region. We got our Lagrange point, we got our bounding hyperbolas, the zero velocity surface. Now we'll squeeze those boundaries down until we produce our strip. This is a homomorphic transformation here. Now we're going to cross this strip with the ring of velocities, which is equivalent to taking a surface of revolution, or a volume of revolution. So we take that upper zero velocity surface and we revolve it about the lower zero velocity surface, and that produces the pipe, as you see here. Now all of phase space in the equilibrium region maps to the volume contained within this pipe, and this provides the natural topology with which we can view trajectories in this space. So what do the trajectories look like in this region? We have our manifolds on the left here in configuration space labeled 1 through 4. If I apply the cylindrical isomorphic mapping to them and plot them in the pipe topology, the same manifolds labeled 1 through 4 appear here. Again, recall that the axis of the pipe is simply equal to your x variable. So the manifolds evolve along the axis of the pipe and they retain their tube-like structure. So this is a relatively intuitive space to work with. A couple of important observations are readily seen now. Near the Lyapunov orbit, the manifolds fill up the entire pipe and thus all of phase space, and this has important implications on the nature of flow. Additionally, we can see that the stable manifolds, in fact, in phase space attach directly to the unstable manifolds, and that the boundary between them, the gateway between them, is the Lyapunov orbit. It's kind of hard to see here in black, and it's also then the gateway between the realms of motion. So we've already gotten a great deal of insight just by visualizing the manifolds in this way, but we can see these insights even more clearly if we imagine cutting our pipe here along the Lyapunov orbit and looking just at the manifolds labeled 1 and 2. That produces the following pictures. So now looking down the barrel of the pipe at this cross-section, you can more readily see that yes, in fact, the manifolds are filling up all of the pipe except for these white spaces here. Those white spaces actually correspond to the interior of the manifolds themselves. Thus you can see, if I want to move from this side of the pipe, so one side of the equilibrium region, to the other side of the pipe, the only transit path available to me is inside the invariant manifold tubes. And this is how and why manifolds govern the flow. The only transit path in phase space is through the tubes. So not only have we gotten insight into the nature of flow, by finding the proper topology with which to visualize this region, we've enabled numerical investigation of the nonlinear equations of motion directly. We don't have to rely on the linearized case. The result of that study then led to 4 key propositions concerning the role of invariant manifolds. Now 3 of those propositions deal with projective geometry, and I don't have time to get into them today, but I'm going to focus on the 4th and most important proposition, which concerns the energy range over which these manifolds are going to govern the flow. Of course, the first part of that is understanding when do Conley's foundational theorems hold. The qualitative picture we see here will hold so long as the tangency condition is met. Now the tangency condition states that one of the manifold filaments must touch the zero velocity surface. And Conley was actually able to prove that is the case through his linearized results. So if we can find an energy range over which this picture qualitatively changes, that is the tangency condition breaks down, we can set an upper bound on Conley's theorems. So to do this, we produce manifolds in the Sun-Jupiter system across a range of energy levels, a range of Jacobi constants. And the important observation here is that a minimum velocity of 0 can only be achieved, that is a minimum velocity on the manifold tube, that can only be achieved along the zero velocity surface. So if you find the minimum velocity is 0, the tangency condition is being met. So if you look at the result of that study, at the higher Jacobi constants, that is the lower energies here, near the equilibrium point, we have minimum velocities of 0 that I can vanish with my algorithm. But then around 3.002, we see the manifold physically detach itself from the zero velocity surface. Now this is a direct contradiction of Conley's linearized proof. Clearly, in this energy regime, the nonlinear space is no longer homeomorphic to that linear space, and Conley's theorems have broken down. Now I want to be very clear. That does not mean that manifolds don't govern the flow in this energy regime. It simply means that Conley's theorems no longer provide a theoretical justification for that governance. And that brings me to my proposition, which states that invariant manifolds govern transit orbits at least in this energy range from C of L1 through C of L5. That is the entire energy regime over which the forbidden region exists, and this extends actually well above the energy range I just demonstrated that Conley's theorems break down. So to validate this, I integrated 5.44 million trajectories across 2,700 mu-c pairs, where mu is the mass parameter, so a given physical system, and c is your energy level. I considered c in the specified range, and then mu from a very small solar system body all the way up to a binary star system. For each mu-c pair, I then seeded 2,000 initial conditions in the pipe section in the interior region, and then back propagated those trajectories in time, recording whether a transit of the equilibrium region was made. I can then compare the transit and the non-transit orbits to the invariant manifolds. Now recall, the key property of the manifold is its separatrix behavior. If I can show that the manifold is separating the transit and non-transit orbits, I can deem it to be governing the flow. And for the proposition to hold, it needs to hold across all energies and all mass parameters. Yes?
So is this a theoretical proof or a numerical proof?
It's a numerical, yeah. We can talk about that more. Okay, so here's the initial condition seeding to see how this is actually done. we have our Lyapunov orbit here. I see the initial conditions in the interior region here, and then along this line. As viewed in the pipe topology, the initial conditions look like this, where I've only seeded the left half of the pipe, because seeding the right half of the pipe, these trajectories will first map to the left half of the pipe before reaching the equilibrium region, so they're redundant to test.
This is an example where this hasn't detached yet, right?
Yes, yeah, this is an energy level where somewhere around here the tangency condition is being held. So this is at one of the lower energies, but just for an example of the setup. So then you can record whether those initial conditions make a transit of the equilibrium region or they fail to make a transit. So we have an example here of transit trajectories in blue. You can see that they're crossing the equilibrium region across the Lyapunov orbit. And then in brown I have examples of trajectories which were flagged as non-transit. You can see they failed to make it across the equilibrium region. I can then color code my initial conditions in the pipe section according to their ultimate behavior. Blue for transit and brown for non-transit. What we can see in this particular example is that the unstable manifold is dividing the transit and the non-transit orbits, so it's acting as a separatrix of motion. So for this particular example, I can deem the manifold to be governing the flow. For the proposition to hold, I need to show this across all of my tested cases. To do that, that's a lot of data to digest, and one of the ways that you can process this a little bit easier is to put it into movies, where each movie corresponds to a given physical system, so a given mass parameter mu, such as the Sun-Earth system, and each frame of the movie corresponds to a given energy level. So here's a movie for a mass parameter similar to the Sun-Earth system. We have on the left-hand side just the transit orbits as compared to the manifold, and on the right-hand side just the non-transit orbits as compared to the manifold. If I play the movie, the energy will increase through my range, and you can see that the manifolds twist and churn in the section, but across all the tested energy levels, every trajectory which we flagged as transit was found inside the manifold, and every trajectory which we flagged as non-transit was found outside the manifold tubes. And you can see that because it's held across all the energy levels, in this regime, for the Sun-Earth system, the manifolds are governing the flow. Here's another example, this time in the Sun-Jupiter system here. Again, we got transit on the left and non-transit on the right. You can see now the manifolds fill up a larger percentage of phase space, and they twist and churn a little bit less in this section. But again, the same qualitative result is held. We can see that 100% of our transit orbits are inside the invariant manifold tubes, and 100% of our non-transit orbits are outside the invariant manifold tube. So again, we see it holding in the Sun-Jupiter case. Now, moreover, we see this to be true across all 5.44 million tested trajectories and across all 2,700 mu-C pairs. And so we use this to say that our proposition is verified. And in fact, manifolds are governing the flow across this entire energy regime, even that regime after which Conley's theorems have broken down. Now, I think this is a very important result. We often use the term low energy design as synonymous with a multibody design, and this is in part because Conley's foundational theorems hold only at those low energies close to the equilibrium point. But this result shows that, in fact, the manifolds are governing flow even at the higher energies, and so we should be therefore applying this to a wider range of applications. So with that, let's turn our attention now to the four-body problem. One of the things that makes the four-body problem so interesting is the emergence of a new class of transit orbit. So I can consider an energy level in the three-body problem where that L2 neck is closed, so transit is not possible through that region. If I take this initial condition here and I integrate it in the three-body case, you can see it bounces off this space and heads out the L1 neck. Now, under the influence of the four-body problem here, if I take that same initial condition, the L2 neck has been perturbed open by that third primary, and that same initial condition will actually pass through that region of space. So that's a new class of transit orbit that does not exist at this energy level in the three-body problem. The question is, what structures control this new class of transit orbit? Now, there's been some preliminary work that uses Lagrange coherent structures to answer this question, in which you find structures analogous to invariant manifolds in a time-varying potential field like that of the four-body problem. Now, the downside of a Lagrange coherent structure approach is that it's computationally very expensive, so it's not particularly well suited to the early stages of mission design where we want rapid and well-informed design iteration. But we can greatly improve upon this by leveraging our understanding of the topology of the equilibrium region. And to do that, we need to understand the importance of the energy manifold. What you see here on the right-hand side is the effective potential function of the three-body problem in the region around M2, and the green plane corresponds to a given energy level. It's the energy plane. Now you can see that the projection of the energy manifold into configuration space, which gives you the region of allowable motion, the projection of that energy manifold is given by the projection of the effective potential function onto the energy plane. So as I raise this green plane, the L1 and L2 necks will open, and as I lower it, they will close again. And this has important implications on the qualitative nature of the flow in these regions of space. So the question is, how does this picture fundamentally change under the perturbations of a third primary M3? Now the slope of the effective potential function, so the shape of these hills, is proportional to mu over r squared. In the region around M2, mu3 over r3 squared is much, much smaller than mu2 over r2 squared. Thus the shape of this hill is essentially unchanged by M3, and this is usually the justification to ignore that force in the first place. However, we're dealing with a chaotic system, so even small changes can be significant, particularly in the energy level where a small perturbation can cause that neck to open and close, as we saw in the previous slide. If we look at the energy plane, that energy level is proportional to mu over r. And so while we could ignore mu over r3 squared, mu3 over r3 is not negligible. But the key observation here is that in the region around M2, the four-body problem looks very, very much like a three-body problem of a perturbed energy level. And we can use this insight now to develop an approximation of the four-body problem as a three-body problem of a perturbed energy level, and we call that approximation the effective three-body problem. So our goal is to find that perturbed energy level such that the dynamics of that approximate problem closely resemble the dynamics of the four-body case. So we can assume that we begin at some initial condition arbitrarily placed in the region around M2, and it flows to some final region of interest xt. Let's assume that that motion is contained to the vicinity around M2, and that the time it takes to move from x0 to xt is short with respect to the synodic period of M3 and M2. Now, in general, energy will not be conserved in the four-body problem, and the change in energy in moving from x0 to xt in the four-body problem is given by this expression here. Now, under our assumption of a small period of time with respect to the synodic period of M3 and M2, M3 will remain essentially fixed in configuration space. In that case, we can treat it as a conservative potential field. So over that short period of time, energy is approximately conserved. We'll simply set it equal to 0 now, the change in energy, and the expression reduces to the following. Now we're trying to find a representation of a three-body problem, so it behooves us to rewrite this expression in terms of three-body parameters, and we can do that using an identity which relates the four-body effective potential function and the three-body effective potential function. And now you can observe that this quantity simply corresponds to the energy level as seen by a three-body observer looking at your initial condition x0, and this quantity corresponds to the energy level as seen by a three-body observer looking at the final state xt. Now, if you move at constant energy in the four-body problem, in general, energy will not be conserved in the three-body case. So the three-body observer will see a change in energy level from this x0 to that xt, and that gives insight into what M3 is really doing to the flow. It's acting as a perturbation to your energy level, to this new energy level C effective, which is the energy level of the effective three-body problem, and we can solve for it by simply rearranging the equation. We can model this energy change now as a small delta V kick on the system. So to produce the effective three-body approximation, we simply perturb the velocity vector of our initial condition until its energy matches C effective. The resulting trajectory, when integrated under mu of the three-body problem, will closely resemble the dynamics of the four-body problem then. This may not be intuitive from this derivation, so I'm going to show a couple of examples now that this is indeed the case. So one of the things we can do is compare trajectories integrated in the three-body problem and the effective three-body problem as compared to a four-body problem, which serves as a truth metric. So we seeded initial conditions in the region around M2 and integrated them through time. If you look at the qualitative flow here for one particular example energy level, at this low energy level, again, the L2 neck is closed in the three-body case but open in the four-body. So the three-body cannot qualitatively capture the nature of those solutions. However, our effective three-body problem has a perturbed energy level which causes that L2 neck to open, so we're trying to resemble the energy manifold in this region of space. So now the effective three-body problem is qualitatively capturing the nature of that flow. To put a couple of numbers on it, across all the energy levels, so this is just one particular energy level tested, across all the energy levels we saw a 3 order of magnitude improvement in median error. So error here is measured, by the way, as a drift error. You look at the final states of the trajectories over your fixed period of time and you see how much did they drift. To put some numbers on it, if we focus just on the L2 transit orbits here, and we look at the Jupiter, Europa, Ganymede four-body problem. After propagating trajectories in the four-body case for around 70,000 kilometers, we saw a drift error of 3,000 kilometers in the three-body problem, and a drift error of only 60 kilometers in the effective three-body problem. So a substantial reduction in error that shows us that the effective three-body problem is faithfully capturing those dynamics. Moreover, now that we have a three-body problem that approximates the four-body dynamics, we can apply now all of our three-body analysis and design tools, such as invariant manifolds. So if we look at those transit orbits of the four-body problem here in red and the non-transit orbits of that four-body problem here in brown, we can compare them to the manifolds of the effective three-body problem. What you can see in this plot is that the effective three-body problem manifolds are actually acting as a separatrix of motion in the four-body case. This allows us to say that the four-body problem transit orbits are being governed by the manifolds of that effective three-body problem. Now this essentially reduces the four-body problem to a three-body problem, and that means that we can take our more complicated four-body analysis and design challenge and apply a much simpler three-body analysis and design challenge without sacrificing the dynamics of the four-body problem significantly and without extreme additions into our computation cost. With that, let's now take these insights and apply them to a practical example in the form of the Europa lander mission design. So at its heart, the Europa lander mission is a search for life, a life on the surface or the subsurface of Europa. So we want to search for biosignatures, characterize the composition of non-ice subsurface material, and assess, of course, the proximity of liquid water. To achieve this, the mission is broken up into a number of phases. We begin in Earth orbit, undergo a series of planetary flybys to reach the Jovian system, at which point we undergo a resonant tour of the other moons of Jupiter before finally reaching the Europa region itself. Once we reach Europa, the spacecraft will split into two. A lander will be sent down to the surface of Europa, and a carrier will be placed into a relay orbit for scientific observations and communications. Now, today I will focus just on the landing phase in which we send the lander down to the surface, and the end-of-life phase in which we ensure that the carrier does not contaminate the surface of Europa. So I just want to talk about some of the mission requirements here, specifically for the landing phase. These are some of the more important things. We want a staging orbit to decouple the Europa approach and the Europa landing phases. So that Europa approach phase is the resonant tours of the moons. The reason you want to decouple these different legs is that such a large and complicated mission will have multiple teams of engineers working on it, and you want the ability to independently and simultaneously design the phases of your mission. And a staging orbit which decouples the approach phase does just that. Additionally, a staging orbit preserves mission flexibility. From that staging orbit, I can execute any number of a priori designed mission profiles as I get updated information in real time that may change my objectives. We want to explore different landing sites on the surface of Europa. We're still very much in the early stages of the mission design process, and while the scientists have some ideas of landing sites of interest, generally our goal as mission design engineers here is to explore the trade space globally so we can assess what we can reach. We need carrier visibility of the lander during the landing phase. So this is a navigation requirement in the case of an off-nominal trajectory. After the two spacecraft separate, we want to be able to watch the lander to see what happens in case errors begin to build in its descent. We need carrier daily visibility of the landing zone as well. So every 24-hour relay orbit, we want at least 10 hours of visibility. Now that 24-hour constraint actually comes from mission operations teams. We as humans operate on a 24-hour cycle, so our mission operators would prefer that we have a 24-hour orbit as well. Then we have our sort of standard trajectory design constraints that we think of, our maneuver constraints in magnitude, frequency, timing, the total number of maneuvers. So for the landing phase, we were given a budget of around 150 meters per second to send the lander down to the surface and the carrier to its relay orbit. As you will see shortly, this proves to be a challenging budget. Then we have a divert delta V constraint. So the divert delta V is the maneuver which sends the lander down to the surface and the carrier towards its relay orbit. Ideally, we want this to occur as close as possible to the landing event. Again, this is a navigation requirement to prevent error accumulation in that landing trajectory. Finally, we have other station keeping and navigation requirements. So the challenge here is that at this stage of the mission design, the constraints are often changing. So it's not particularly useful to try to fully optimize any one design, but instead we seek a method to rapidly explore the trade space. Now the structures of the multi-body environment provides a mechanism by which we can rapidly explore this space and still have relatively well-informed designs as our manifolds are leveraging the dynamics of the multi-body environment. Additionally, of course, we have constraints which may not be feasible and constraints which are competing. So one of the things I want to do today is highlight some of the key trade-offs in the design space. So we can consider first a two-body baseline design to get some perspective on the mission. So we're considering staging orbits of Lagrange points, which do not exist in the two-body problem, but we can most closely approximate them as circular orbits with a radius equal to that of the Lagrange point of interest, as indicated here by the dashed line. For a relay orbit, we consider a 24-hour period circular orbit, which provides good coverage of any site on the surface of Europa. In moving between two circular orbits of these radii, the optimal transfer is well known to be a Hohmann transfer, and then we can use a similar burn to send the lander down to the surface. So we have a series of 3 burns with a total mission cost now of 402 meters per second. Recall that our total delta V budget is only 150 meters per second, so this is well above that, and we need significant improvements if we're to realize our mission constraints. To see the challenge, we can look at the landing leg here, and you observe that this is the driving cost of the mission, 272 meters per second of that total mission cost. And so now we can look to nature for inspiration and leverage the dynamics of the multi-body environment. The idea here is that landing is nothing but a controlled impact, and comets and asteroids reveal low-cost pathways through space with complex itineraries, including impact or, equivalently, landing trajectories. A great example is Shoemaker-Levy 9. I don't have time to go into the details today, but one of the things I also showed in my work is that the comet Shoemaker-Levy 9, shown here in blue, was actually captured by the manifolds of Jupiter, ultimately leading to its impact. Now, comets like Shoemaker-Levy 9 have no onboard thrusters, so they're executing these itineraries for zero cost. So the idea is that manifolds are revealing zero-cost pathways through space, which we can use to move from our staging orbit to the surface. And that's the crux of our manifold-informed design approach. So we begin with generating our libration point orbits, our Lyapunov orbits, our halo orbits, and so on. We construct their invariant manifolds, and we map all of the trajectories as they impact the surface. Each impact corresponds to a potential zero-cost transfer to some region of interest. So for example, if I want to hit the landing zone at 140 degrees west longitude, I can predict this particular manifold filament, and that is a zero-cost transfer where we're leveraging the perturbations of the multi-body environment to trade time of flight for the fuel savings. To then achieve the relay orbit, I developed a local optimization tool which solves a series of 2-point boundary value problems. I have an outer loop and an inner loop to determine the optimal departure point on this landing trajectory, the optimal insertion point in the relay orbit, and then the optimal time of flight. And this gives a method for us to rapidly explore the trade space. So here's a design doing just that, where we're targeting a 24-hour spindle orbit here around Europa. We begin in our Lyapunov staging orbit, and we select our impacting manifold filament that reaches the surface. Again, that is done for zero deterministic delta V. So we coast along this trajectory, then the lander is going to be sent down to the surface for no cost. Now we have to perform a maneuver to send our carrier orbit towards the relay orbit, or sorry, carrier trajectory, and then a second maneuver to actually insert the carrier into the desired orbit. So now we have a 2-burn solution with a total cost of 84 meters per second. That's an 80% reduction in delta V as compared to the 2-body baseline design. Such a substantial improvement in fuel savings that we actually go from an infeasible mission architecture down to a feasible mission architecture, and that's because we've leveraged the dynamics of the multi-body environment. Now there are of course some challenges with this particular design. In particular, we don't have a good view of the landing event. The position of the lander x bar sub L here during the landing event is given, or sorry, the position of the carrier during the landing event is given here. It's not until about 3 hours or so after landing that we can see the landing site, which is undesirable from a navigation standpoint. Fortunately, we have extra delta V left in our budget, so we could attempt to expend more fuel to phase ourselves more appropriately, but we can also trade off time of flight. So again, we can now target a 24-hour relay orbit. We begin in our staging orbit here, and we send the lander down on an impacting manifold filament. This time we'll do our divert maneuver much earlier, and that will allow us to properly phase ourselves. So in this case, as you can see by x bar sub L, we have a very good viewing opportunity of the landing event. The particular challenge with this design is we have a very long drift time, so the lander is going to drift on its own for 53 hours before reaching the surface. In practice, over such a long period of time, the lander will need to perform its own trajectory correction maneuvers. So we'll have to make sure now that the lander is outfitted with the capability to do that. So while our trajectory design cost has not gone up, only 96 meters per second, again well below the 2-body baseline, the total cost of the mission in terms of dollars could go up because you have to add this extra infrastructure. So it depends on what you care about more. And this illustrates one of the trade-offs in the space, which is the view of the landing event and the separation time that you make your divert maneuver. All right, I'm starting to run short on time here, so I'll go more quickly. I have just finally the end-of-life strategy, where we are going to try to send the carrier into a graveyard orbit such that it never contaminates the surface of Europa. We can consider an initial condition here in the region around Europa. We perform a maneuver to escape through the L2 neck, and then another maneuver to reclose that L2 neck. The idea here is that the forbidden region will prevent the carrier from returning to the surface of Europa, and therefore it cannot contaminate. Now, from our study of the four-body problem, we know that in the Jupiter-Europa-Ganymede four-body problem, the perturbations of Ganymede will cause this neck to fluctuate. So we need to account for that fact in our design process. But we can not only account for it, we can actually leverage it directly in the design. And the effective three-body approximation I derived earlier provides a disciplined way to not only quantify the magnitude of those perturbations, but a methodology with which to leverage them in the design process. So we can consider a relay orbit at the beginning of the end-of-life phase here, such that the L2 neck is closed in the three-body problem. Now, if we were to do a pure three-body design, we'd have to perform a maneuver to open the neck and then another maneuver to reclose it, which is inefficient. Under the perturbations of Ganymede, this neck will open up. And when it does open up, the stable manifold of the effective three-body problem will appear. And we can simply perform a maneuver which targets this manifold, and it'll allow us to escape leveraging the dynamics of the four-body problem. Here's an example design which does just that, where we perform a maneuver here that targets the stable manifold of the three-body problem, as you can see here in the plot. Now, this is done all the while the three-body neck remains closed. So it's a mission architecture which is not possible in the three-body case without expending additional fuel. I showed this as a three-body manifold, but I'm just using that for design. This blue trajectory is actually integrated in the true four-body problem, so it is a four-body escape technique, and the manifold just provides a disciplined design approach. By leveraging these perturbations, we got an additional fuel savings around the order of 5%, depending on the particular design, and that's on top of the three-body problem. Of course, this is leveraging only one perturbation, one delta V kick of Ganymede, but we can leverage successive perturbations to improve this design. So for example, we can begin in some initial orbit here in black, and then every 7 days Ganymede flies by the L2 neck and perturbs our orbit, and we can use that delta V kick to go through a sequence of intermediate orbits shown here in red until we achieve this final orbit in blue. What's special about that orbit is that it passes through the L2 neck for free under the final pass of Ganymede. So this is done with no deterministic delta V. The reason it's accomplished, of course, is it's using the stable manifold of the effective three-body problem. So we have our final orbit here in blue, and if we look at a section here with the manifold, we can see it lies on the surface of the manifold, which is why it escapes. So this required 59 successive perturbations of Ganymede to achieve, which takes a long time, but we can add small additional maneuvers to reduce that time of flight, and that's really the key trade-off in these multi-body analysis and design problems. You're trading off time of flight for fuel. So with that, let me summarize what I've shown you today. I presented a study of the topology of the equilibrium regions of both the three-body and four-body problems. In doing so, I set an upper bound on the energy range over which Conley's foundational theorems hold, and demonstrated that in fact manifolds govern the flow over a much larger range of energies than previously proven. And this opens up manifolds to a wider range of applications. Second, I derived a method to approximate that four-body problem as an effective three-body problem of a perturbed energy level, and show that the manifolds of that effective three-body problem actually govern transit orbits of the four-body case. And this shows that we can take our more complicated four-body analysis and design challenge and reduce it to a simpler three-body analysis and design challenge without adding additional computational cost or sacrificing the dynamics. Finally, I leveraged dynamical structures of both the three-body and four-body cases to design capture, landing, and end-of-life trajectories for the Europa lander mission that significantly outperformed two-body baseline designs. Here are the first author publications that resulted from my investigation. And now I'd like to talk about some directions for future work. So first off, I think it's important that we investigate the very high energy breakdown of manifolds in the three-body problem. Today I presented just the energy range over which the forbidden region exists, but I have a conjecture which states that as long as the topology of the manifolds is preserved, that is, its tube-like structure is preserved, it should continue to govern the flow. However, at the higher energies and higher mass parameters, it's possible that the primaries will shred the manifold tubes, destroying their topological structure. If that's the case, then it will of course break down. But more work is needed to understand what that process looks like, as well as if and when it occurs. Second, I want to investigate the role of manifolds in the spatial problem. So today I consider just the in-plane motion, but when we consider that out-of-plane motion, the problem is much more difficult to solve. The manifolds are still two-dimensional structures, but now they're embedded in a five-dimensional energy surface. A two-dimensional object cannot separate a five-dimensional space. Thus, we can no longer make claims of inside or outside anymore, so we can't apply the results in the same way. However, when we look at the trajectories of comets like Shoemaker-Levy 9, what we see is they appear to be following the manifolds of the spatial problem anyway. So they seem to be playing some kind of a role, but more investigation is needed to understand what that role is. I'd also like to study the effective three-body approximation for other four-body systems. So today I just focused on the Jupiter-Europa-Ganymede four-body problem because this was done in support of the Europa lander mission. However, the domain of that approximation should be a function of the relative sizes of M1, M2, and M3, as well as the relative distances between them. So more work should be done to investigate that domain. And then finally, in the case of the Europa lander mission, I want to explore other landing zones and other constraint relaxations to better understand the trade space. I think it would be also interesting to use some global optimization techniques or try to fully optimize some of these designs. The hope would be that we could then try to make some guarantees about how suboptimal our initial manifold-informed designs actually are. With that, I just want to thank so many people who have helped me along this process. I want to begin with my committee. Thank you to Professor Pate Cornell for graciously agreeing to be the chair today. You were very friendly and accommodating in the stressful scheduling process, so I appreciate that, and thank you for being here. Thank you to Professor Pavone as well for being on the committee. I took your Intro to Optimal Control course my first year at Stanford. It was one of my favorite courses I've ever taken. I was in your office hours just about every week, so thank you for bearing with me in those office hours, and thank you for being here today. Thank you, Professor D'Amico. You have a special place as being the first person to offer me funding here at Stanford. I TA'd his orbital mechanics course here before my fellowship kicked in, and I think it might have been your first teaching experience at Stanford as well. So we had our growing pains together, we went into battle together, and it was such a tremendous opportunity to work with you. I was so excited when Sigrid told me there was an orbital mechanics professor coming to Stanford, so thank you for those experiences and thank you for being here today. Of course, Sigrid, I'll always be so grateful that you took me into your lab. When I came to Stanford, I didn't know what I wanted to work on for sure and who I wanted to work with. And I attended Sigrid's dynamics course, and I was just taken by how passionate she was with the field of dynamics. And I thought, here's someone who loves dynamics as much, if not more, than I do, and that's the type of person I want to work with. And over the years, we've had lots of wonderful conversations about dynamics and dynamical systems, and I'll always treasure those exchanges. I also want to thank you for believing in me and giving me the freedom to explore a topic which, as you stated, is a little far afield of the normal domain of the department, so thank you for that opportunity. Last and certainly not least, I want to thank my co-advisor Martin here. For those of you who don't know, Martin is not a professor here at Stanford. He's a mission design engineer at JPL. But despite that fact, Martin has met with me an average of an hour to an hour and a half every week for the last 4 years. So a tremendous time commitment from his personal life to make this possible. When I began, I was a complete novice in the field of multibody dynamics. I did not understand topology. He gave me private tutoring lessons to get me up to speed on the mathematics. He helped me formulate a research plan and has been just generally a mentor in my research as well as my personal life. I couldn't have done this without him. I'm so grateful for everything you've done for me, Martin. Thank you. I want to thank the staff here at Stanford, Dana, Sharan, Patrick, Robin, and Jenny, for helping with the many administrative hurdles that come with getting a degree here at Stanford. I want to thank my collaborators, Brian Anderson and Robin Woolens in particular, who couldn't be here, but many fruitful conversations with them over the years, as well as John Junkins and Alan Barr. At JPL, I want to thank John Sims, who's the group supervisor of the Outer Planets group at JPL, for allowing me to have 3 wonderful internship opportunities in his section. In that same regard, I want to thank Tim McElrath, who is the manager of the Europa lander design team that I worked on. So thank you, Tim, for the opportunity to work on such an exciting project. I want to thank my wife, Anne, who moved out here so that I could pursue my dreams and passions, and gave up the life in the Midwest that she had wanted. She's always been the support over the years when times were tough with quals or writing my thesis or getting funding. She picked all the extra slack up at home to make that possible. Additionally, she has a very practical hand in this. Everything I've ever written has been vetted through her first. She's a wonderful writer, so this is partly her work as well. So I love you, Anne. I couldn't have done it without you. Thank you. I want to thank my family, my dad and my grandparents who are watching abroad, as well as other family members, and my mom who is here in person today. Particularly my mom, thank you for instilling a passion for academics. I'm told that when I was in first grade, I was resistant to learn how to read. But my mom insisted that reading would be the key to my future. So thank you for convincing me of that and setting me down this path today. I want to thank also all my friends here at Stanford who have made it just such an absolute treat to work and live here at Stanford. And then finally, thanks to the Ennis Fellowship for making this work possible financially. With that, I'll open it up to any questions you might have. Thank you.
Okay, so let's have questions from the audience at this point.
Yeah?
When you studied the 3 and the 4 body problems, you provided a specific motivation of why you wanted to look into that. I'm wondering, do you think there will be any interest in studying an nth body problem? And have you seen any trends with your 3 and 4 body problems that you think someone could take in the future and extrapolate, formulate?
Yeah, that's a great question. I would say yes, it's interesting to look at. I think in the system I looked at with the Jupiter-Europa Ganymede, additional perturbations beyond that point start to drop off even more rapidly, so it probably wouldn't be too important. But if you look at other physical systems in the universe, there might be configurations where it's more effective to add the additional bodies, especially with the study of natural occurring bodies. You know, a small delta V kick that we're seeing here is not that significant in mission design in certain applications, but for a comet with no onboard thrusters, that kick is. Now, the methodology I presented here, I think should be generalizable to the n-body problem if I go back to that slide which shows the energy manifold. So you can simply continue to add bodies and see how the perturbation to both the slope as well as the energy plane itself has changed with the addition of the bodies, and provide a similar derivation to like the one I showed on this slide here that accounts for those effects. I think that in my particular example it wouldn't be significant, but it's something that could be done. Yeah?
Travis, on slide 43,
Okay.
you mentioned, you've got the red lander trajectory
Yes.
that then ends at Europa, and you mentioned, free landing. So do you not have to apply?
Great question. I'm glad someone brought that up. I forgot to mention it in the talk. So when I say a free landing, I'm not reaching the surface with zero relative velocity, if that's the heart of your question there, or you're talking about the departure. Yeah. So really there's a descent team. I'm sending this to a patch point at which a descent team would take over. So I have to send it to that patch point, maybe 50 kilometers, 100 kilometers, something like that above the surface, with some range of relative velocities and flight path angles, additional constraints which I didn't discuss. So we were limited to, I think, 1.95 kilometers per second for that patch point. So it's not a zero velocity. That's why, like in the two-body design, I didn't use another maneuver here to slow it down.
But you did have a limit. You weren't allowed to show up there without...
We weren't allowed to show up there, yeah, like 10 kilometers per second, which in the two-body design does partially limit the space. If you try to burn from that carrier orbit directly, you end up having a higher velocity than if you burn earlier in. And so that's why I had to go to the staging orbit first in the two-body case to meet that constraint.
Thank you.
Yeah.
So in the four-body problem, in your analysis, do you incorporate the period of the fourth body?
Yeah. So in the derivation, it's assumed that the time period over which you're evolving is small, so that I can say it's essentially fixed. So when I produce the manifold, it's sort of like a snapshot of the four-body problem, so at that instant in time. But as long as you transit through that manifold tube in a relatively short period, the gateway will remain open for you. So that's why I say it needs to be short with respect to the synodic period of M2 and M3. Now that being said, look at this trajectory here. It undergoes no less than 4 revolutions around Europa before escaping through that tube. However, my tube is assuming a short period of time. In practice, we can tolerate relatively large periods. I would say up to on the order of maybe half the synodic period, and still with some small trajectory correction maneuvers be okay, less than sub-meter per second type corrections. So you can always use this approximation even on the longer domains. The longer you stretch the time, the more likely the error will accumulate. And then the boundary maybe, so you can think of this now as a fuzzy boundary because the manifold is an approximation. So as time goes, the error bars around the manifold would grow here. Nicholas.
You talked about leveraging the full body to give you this escape at the end of life, but how do you prevent it from being a problem? Or is it
really hard to target that type of?
Okay, that's a great question. So the thing here is that all of these orbits are unstable. So weakly perturbed, they'll start to drift through time. So in general, you'll have a station-keeping budget, which you use to put yourself back onto your orbit. Those maneuvers are not particularly large. It's just that you have to do them with a regular basis, around 3 times per period. So the danger is only a function of the time constant of your system. So here we have a period of the orbit, of Europa of around 3.5 days. So we're going to have to perform maneuvers here probably every day at least to continue to station keep. If the time periods start to go shorter, then it would become infeasible. But in practice, we don't have shorter time periods than this system. Yeah.
So when you were looking at the energy range over which the
manifolds govern the flow.
Yeah, exactly. Of course, that holds. So your tubes are expanding, right? So you're covering the full range between L4 and L5.
Right.
Okay.
Well, I'm covering L4 and L5 have the same energy level. I'm covering the range from L1 all the way up through L5. L1 being the lowest energy, L5 being the highest energy.
Okay, but what I'm saying is...
in configuration space, how much of the...
Yes, I'm saying in physical space, your tubes are sort of expanding to fill that whole region.
Right. That's also, by the way, a function of the mass parameter. So if I have smaller mass parameters like that of like the Sun-Earth system, they grow in size, but they don't completely fill the space. It's when you start to get close to the binary star type systems where those manifolds will like physically be all of space. So at that point you can say like, maybe it's not as useful, but those are particular fringe cases at both very high energy and very mu. But the result is still holding, but you're right, it is a large percentage of space at that point.
When you talked about the Europa liner, all those staging orbit, and you want to escape to like land on the how do you know which orbit you're going to take on the surface of the
Yeah, so how do you mean, how do I know which one to target, or how do I know where I'll end up going from that staging orbit?
I mean, I guess like when do you decide to make a maneuver, like to spawn this one and land at this point?
Yeah, so from our initial global search of the space, I mapped out all of the possible landing trajectories so I could select those candidates. In the practice of the mission, to reach that specific orbit that I've chosen that I'll know will send me to the desired landing site, if I just let myself drift, I'm going to kind of randomly walk along some of these other trajectories. So this is a station keeping maneuver. You would have to perform a maneuver just to stay in the Lyapunov orbit, but if you just barely nick this, you're going to drift off, and you can use that station keeping maneuver rather than to target the orbit to simply target the individual manifold filament. But to know which manifold filament, it just has to be done through a search of all possible candidates. Yeah.
How sensitive is the final solution from your starting point?
So it depends very strongly on which physical systems you're looking at and what type. So in general, the perturbations are very sensitive in the region around the Lagrange point. That's where you're sensitive. By the time you've come back around here, you're almost into essentially a two-body regime, in which case the perturbations are weak. So you can look at the monodromy matrix and get the eigenvalues directly to get some measure of the strength of that perturbation. I don't have that number available off the top of my head, but you can calculate something with that sensitivity. Again, I want to note that those numbers can show great sensitivity, but it's evolving over long time constants, and because of that sensitivity, you actually only need small correction maneuvers to target, even though a small error can drift you away.
Okay, well, thank you, Travis. And
Thank you.
Further questions?
Offline.